Welcome to our second science pub from home. We have Chris Coulter with us, our AV guru. He's been to almost every single one of our science pubs. First and foremost, I want to welcome everyone. I hope everyone is staying safe and well and sane. And I put a couple of links up in our chat. One is a donate button, and we would love to ask. We had a couple of people wonder about if we were going to bring online raffle tickets and what was happening with our raffle. I wanted to let you know that we were trying to work on how we are going to make raffles come to our virtual science pubs. But for right now, if you would like to donate, this is a free public program, and we would love to happily accept your donations to continue keeping this a free public program. So the link is right there. Also, the museum is still open. I know that there may be some confusion with what is closed and what is not, but since we have outdoor, our outdoor portion of the museum is safely open, so you can come and visit us. We have our beautiful butterflies alive, and it is a very zen experience and a very safe experience. So please come and visit us at the Santa Barbara Museum of Natural History. We are open Wednesday through Sunday. So come and see us. And the other link there is for our camps. So camps are happening, and normally camps during the summer is a crazy time and a wonderful time to hear all those kiddos running around the museum campus. But we are doing them safely from home and virtually, and we are getting great feedback. So if you have little kiddos that are really eager and wanting something new, then sign up. We have a couple of spots left. They're running for the rest of the summer, so there's a lot of amazing topics. Wizarding camp and dino camps and bugs camps. So there's something for everyone. Ocean themed camps. So highly recommend those as well. Another thing is Dargan's is still open for takeout. And although we aren't at Dargan's, and we don't see ourselves being at Dargan's for Science Pub for the next little while. So I hope you all are enjoying these virtual science pubs and staying safe in your own home. And we're still bringing the science to you. And Chris Coulter will share his whiskey. So I hope everyone has their lovely drink. Tonight's mashup was, I think we said, grab some bangers and mash and an Irish whiskey, which Chris Coulter has Macallan's going. So, you know, support your local businesses. I know it's really getting really tough out there. So be kind. So with that, I'm going to turn it over to the lovely and kind Chris Coulter.
Lovely and kind.
Yes, well, you are.
I'm glad to be here. Thanks for the introduction. The weather's getting warmer, and you know, I still think that these Mondays, a little bit of whiskey tastes pretty good, especially if it's on good ice. And I was looking at my ice today, and I don't know, it's not very clear. It's sort of cloudy. It's a little clear at the one end, not very clear. It reminded me that I went to Baird Glacier with my brother and on his boat, and we were cruising along, and we reached over and picked up a small piece, about maybe 30-pound piece of an iceberg. And the icebergs were beautiful blue, you know, to look at the big iceberg in the distance. But when you picked up this little piece, it looked like a meteor that had come from outer space, all pockmarked and everything, but it was perfectly clear. And we broke it up, put it in an ice chest, and for days, we had the best ice for our drinks. And I tell you, that glacial ice, almost nothing better. You know, you put 12-year whiskey and then you put a 1,000-year-old ice cube. It's heaven. So that's my, and I'm going to have next week or next month, I'm going to have the method for making your very own clear ice. I'll have a recipe. I'm going to find out all about it because I'm desperate for perfect ice, and that's what I'm going for.
So I actually just watched a YouTube video about clear ice, and I guess the trick is to have it freeze slowly. So if you let it freeze slowly, then the bubbles can get to expel out of the ice, and the ice is super clear. My knowledge ends right there. Thank you, YouTube. So that can be your recipe.
I'll figure it out for you.
Perfect, great. All right, thank you, Chris Coulter. So I wanted to go through before I introduce our speaker for this evening, to chat a little bit about how we will be handling question and answers for this evening. So if you all look at the bottom of your screen, there are a couple of different buttons. One should say question and answer. And that's how we will be working on answering your questions this evening. There is a chat box as well, and I will be looking at that, but mainly I will be looking at the question and answer box and then asking it to Alan after his talk. And he'll be answering as many questions as we have until our time runs out. And then if you have any further questions, you can go ahead and email those to me and we can follow up with you later. So the chat is great, and I can actually see some people chatting right now. Sabina and Judith, thanks so much, and go ahead for sure, chit chat with us. And if you have questions for your other attendees, that's a great place to use it. But the question and answer box is how we'll be going and utilizing the portion of question and answer portion for this evening. So now getting to the good stuff. So Alan Holmes is currently the president of Cloudland Instruments, a small company in Santa Barbara, specifically organized to build 2 ocean color measuring satellite instruments called Hawkeyes, which we will be hearing about more in this talk momentarily. Prior to this, Alan was the founder, president, and director of research for Santa Barbara Instrument Group, a company specializing in developing CCD cameras and instrumentation for both amateur and professional astronomy markets. Dr. Holmes has also worked for Santa Barbara Research Center in Goleta and Ball Aerospace in Boulder, Colorado on several space missions. He was a system engineer for the Sea Viewing Wide Field Spectrometer, the Tropical Rainfall Mapping Mission Visible Infrared Spectrometer, and the Landsat 6. While in college at University of Arizona, Alan assisted with assembly and calibration of large probe solar flux radiometer and the Pioneer Venus, which reached the surface of Venus in 1978. While at Arizona, Alan obtained his master's and Ph.D. in optical sciences and a BS degree in engineering physics. Alan is married to his wife, Dorothy, a medical doctor, and has 2 sons, Michael, a dentist, and Patrick, a mechanical engineering student at the University of Michigan. His family enjoys traveling and has visited many countries around the globe. Without further ado, Dr. Alan Holmes. So we are going to turn it over to you, Dr. Alan Holmes.
Thank you, Stephanie. Nice introduction there. I wanted to talk about my experience in basically starting from a very modest, small beginning, ending up with a satellite in orbit, basically starting an aerospace company at the age of 65, which is not something many people do, or not even something I'd probably recommend, actually. So I'll put up my slides starting now, then. All right, this is a picture of me when we finished the 2 satellite instruments. The 2 instruments are in my hands at this point. So it's kind of a circuitous route. Back in 1991, I started working on the SeaWIFS mission, which was the Sea Viewing Wide Field Spectrometer for SBRC. I was a systems engineer. And it was about a 2-year development, and we shipped it and eventually flew. It lasted 10 years in orbit. The instrument was working fine at the end, but the spacecraft bus had some problems, which led to the whole thing being turned off after 10 years. But that was my introduction to ocean color way back. This poster was generated by Goddard Space Flight Center personnel back in the SeaWIFS day. Ocean color, most people's first question is, who cares? And it turns out there's about 3,000 people in the world that make a living off of ocean color. And one of the major impetuses for this kind of research is to measure chlorophyll and phytoplankton in the ocean. Phytoplankton are the little microscopic animals that are at the bottom of the food chain in the ocean, and they basically have chlorophyll to absorb sunlight and build their exoskeleton. Now, the interesting thing about this is this is one of the processes that takes carbon dioxide out of the atmosphere. So this is what they call a carbon dioxide sink instead of a source. So at the time of sea whiffs, NASA was trying to get a handle on how much carbon dioxide the oceans absorb every year. And that's kind of part of the motivation for it. The other that was publicized at the time is the fish in the ocean tend to follow the phytoplankton, plankton blooms, because that's where the nutrients are. So the secondary goal was fish finding for large commercial fishing vessels. Not sure that ever got its legs under it, but that was one of the reasons for the instrument. As a result of working on this instrument back in 1991 and staying involved with the community for other reasons over the last 30 years, I got to know a lot of the people in America who actually do ocean color for a living. This is a group we got together back at Goddard Space Flight Center. And I'm the person in blue that's third from the left, but I wanted everybody to take 30 seconds and try to figure out who in this room is the NASA astronaut that has flown in space twice. This is always a trick question, a good challenge for everyone. The person has since retired, but which person was a NASA astronaut? Anyway, now that you've all made your guess, it's the small woman in front on the right wearing a green blouse who's in front of my very tall friend Hessel. Anyway, her name is Mary Cleve. She flew twice. And the second question is, who is the most politically powerful person in this photograph? And the answer is the woman on the right, Paula Bantepi, who basically controls all the money. So she's an important person. Fortunately, my project did not require any NASA funding, so I didn't have to jump through any of those hoops. While I'm at it, the person directly to my right in the picture with his arm around me is Gene Feldman, who's the NASA contact analyzing the data, and you'll hear his name later. And the person to the right of my astronaut friend is John Morrison, who's at the University of North Carolina, and it's his program, basically. So we delivered SeaWhiffs in 1992 or 3, and in 1995, I left SBRC and I started a company called Santa Barbara Instrument Group. Santa Barbara Instrument Group made low light level CCD cameras for amateur astronomers. This is basically a digital camera for amateur astronomers, and we sold them worldwide. Actually, I started the company in 1989, and for those of you as old as I am, that's back when a really good computer had 1 megabyte of RAM and Hercules graphics. So our CCD camera product line kind of matured right along with the computer industry, and we did fairly well. This is a good image taken by one of our users in Northern California. And the little blue nebula in the lower left, that's called the Soap Bubble Nebula, was actually discovered by amateur astronomers. It had been unknown to science until amateurs started taking these very deep pictures. Both this object on the right that looks nice and bright is almost invisible in a telescope. These things are very faint. As a result of digital imaging and CCD cameras emerging in the amateur astronomy workplace, anything that the 200-inch telescope could have accomplished in 1980 can now be done by an amateur in his backyard for a modest cost on the order of $10,000 to $15,000. So it was kind of a revolution in its time. Ended up selling the company in 2011 and worked at it for another 4 years, and in 2015 retired from it. As a result of my association with SBIG for 26 years, I was very active, and I think I talked to almost most of the serious amateurs on the planet. We sold worldwide. We, at the beginning of our sales, were almost the only game in town, so talked to a lot of people. And one day I got called by a customer named Adriana Sherman in Guatemala. And she stood out because only like 1 to 2% of our customers are women. And also she started out the conversation complaining she couldn't get good customer support. Nobody could answer her questions. So I felt bad. So we started talking. Turns out Adriana and Andy Sherman live in Guatemala. He was a Peace Corps volunteer and met her when he was back in his college age. And it turned out she then invited me to her lake house in Guatemala to see her observatory and just to visit. And I didn't realize quite what I was getting into, but she had a bulletproof SUV pick me up at the airport in Guatemala City, took me over to the helicopter port, where we got on her helicopter and we flew to her house in Lake Atitlan, which is a beautiful house, infinity pool and all that, looking out over the lake. I was very impressed. It turns out her money, a large part of it is derived from a rubber plantation she owns, not a couple hours away from Lake Atitlan. But she has 11 square miles of rubber trees, and I toured that, but that's a discussion for another day. But this was our first trip to Lake Atitlan, and it's one of the most beautiful places on the planet. It's just amazing, spectacular view. It's surrounded by these they're not extinct, they're basically quiet volcanoes. And the lake itself is at almost 7,000 feet elevation. So even though you're in the tropics, it's got a very comfortable climate. So it's one of the most beautiful places on the planet, but I think back in early 2000s, a hurricane destroyed the sewer system of all the local villages. There's like a dozen, mostly Indian villages around the lake. So all the sewage just washes into the lake. The lake has no outlet. It's basically a basin. So you can't swim in those waters. And in 2009, the local Indians discovered cheap Chinese fertilizer, became very available, and they all rushed out and got it. And most of them over-fertilized their fields because they were not familiar with it. And all the excess fertilizer washed into the lake, and the lake turned green and smelly with the algae, and a lot of fish floated to the surface. And it got pretty nasty, according to Andy and Adriana. And they started a group to try to save the lake. And it's about that time that they contacted me and made all these comments. Well, I happened to run into Gene Feldman from NASA on a vacation and started a conversation about this after that event. I complained that all the NASA missions were global and the satellites didn't have resolution adequate to properly see a lake like Lake Atitlan. Even though it's 30 miles long, that's still pretty small from orbit. So I suggested that they needed an instrument that could look at smaller bodies of water, like rivers, estuaries, and areas close to the coastline. After all, I think 90% of people in America live within 50 miles of the coast. So Gene's friend, John Morrison at the University of North Carolina, Wilmington, was looking for a project in January 2012. And the result, after 2 years, was something called SOCON, Sustained Ocean Color Observation from Nanosatellites. So at this point, we had been searching for funding for about 3 years, but it turned out that the Gordon and Betty Moore Foundation, Gordon Moore of Intel fame, he has a large amount of money, and he had a Marine Sciences Foundation that distributes millions of dollars a year. And we proposed a CubeSat mission to him. And Gordon liked the idea. He read our proposal the day of Thanksgiving dinner in 2014. I think he was like 85 at the time, and he just made a call the next day and started it all happening. It sort of fit with his whole philosophy of Moore's Law of, as time goes on, things get smaller and cheaper and lighter. So I think that's what appealed to him about ocean color being a small instrument. So my company, Cloudland Instruments, was to build the instrument, and the Clyde Space in Glasgow, Scotland, was to build the spacecraft bus. And the spacecraft bus is the part of the spacecraft that provides power, communications, attitude control, radio link to the ground, everything. So our funding was $763,000 for 2 instruments. And the instrument name was Hawkeye, which John Morrison picked, flying on the SeaHawk satellite. Seahawks are a popular bird in North Carolina. I think that's where he got the idea. So at that point, we had funding, so I went out and rented space off Castilian and hired 4 engineers. My company, SBIG, was being moved at the time to Ottawa, Canada. So it was a good time because everybody was a bit idle. So 3 of my engineers from SBIG joined me at Cloudland: Craig Heron, Linda Sasaki, and Matt Longmire. Now, talk a little bit about a 3U CubeSat. Excuse me just a second. They size CubeSats in terms of U, where U is unit. And a unit is a 4 by 4 by 4 inch cube. And a 3U is 4 by 4 by 12. And that's me holding the frame in one hand and a picture of it on the right. And the intent was the spacecraft would fly with the solar panels in the direction of flight, and we would be looking down. And there's a GPS antenna on the top that figures out exactly where the CubeSat is, and some antennas and such. So here's the portion of the instrument that we had to work with. Basically, we got a 4 by 4 by 4 inch cube. I should comment on this. This actually caused me a lot of aggravation because when I started, we were 100 millimeters on a side. And then it was 96 millimeters on a side. And then 6 months into the program, it was 94 millimeters on the side. And then like 6 months later in the program, we were squeezed down to 92 millimeters on a side, which doesn't sound so much, but we were really stretched on space. And every time my envelope got shrank, Linda had to redesign all the mechanics for a smaller package. Here's the final instrument. I'll not go too much into the technical details, but we had, at the bottom, we had 4 linear arrays of the type you would find in a document scanner. And the instrument's sensitive in 8 spectral bands. It senses down into the deep blue wavelengths, red, green, and the near infrared, and a total of 8 different wavelengths. And I'll talk a little bit about why 8 later. So we didn't have much space, so I had to put 2 bands per linear array and designed some optics to go with it and sized it all to fit. So each linear array is fed by 2 lens assemblies. And then there's a filter which defines the passband, whether it's blue, red, or green. And then there's a scrambler which reduces the effect of polarized light. Those of you who used cameras to photograph landscapes, you probably have a polarizer to darken the sky. Well, the reason that works is because the sky is strongly polarized, and the ocean color people don't want to be sensitive to the polarization state. They just want to know energy. So I have to put in a scrambler to make it insensitive. So I did the optical design on this. My background's in optics, so I designed up a lens and contacted a company I knew in Singapore to have it made. We were real cramped on space, and I was kind of hurting for light too, so everything just barely worked at this point. And one more technical note, here's a picture of the linear array we used. I'll not say much about this. It had basically 4,000 pixels across, and we used 2 sections of it. So I had 1,800 pixels wide per band times 6,000 rows for an image. This instrument works in what's called push broom mode. So the instrument flies along and we basically have like a push broom scanning the ground. Sorry, this gets a little technical here. We're almost done with this part though. Anyway, here's some details of it. You basically have to cram all this in a 4x4-inch cube. We have some space for some boards. I had to have a shutter to be able to close this thing off and find out what the dark level of the electronics was. So it's pretty small. And we delivered it to Clyde Space in Scotland. And this is the instrument, which is on the right with the gold-colored sides, being integrated into the rest of the satellite. They bring out a lot of test points because they were checking everything out at this point, still developing their software and such things. Pretty busy. There's actually a lot of things going on inside a fairly small box for this instrument. And the finished satellite looks as shown here. And this would be with all 4 panels deployed. Okay. Now, to say this is small, I need to put up a chart showing what small means. On the far left, you can see the size of the SeaHawk Hawkeye satellite. And on next to it, you see SeaWiFs that I flew, that I worked on before, and that instrument was 200 pounds. And even then, that was pretty small. If you look back at a lot of the other instruments that have flown, it makes you worry about one of these things coming down in your backyard. There are really a lot of very heavy objects up there. So we are a lot smaller. I'll compare our images with Modus Terra in a little bit, which is quite a bit larger. We did a lot of our early testing outdoors. We mounted the instrument on a rotary scan table. And here it is with Matt Longmire running the computer. We clamped it to the railing of someone's house and we basically would scan, in this case, Goleta, while collecting data. This is the location we had. My accountant at the time was renting an apartment with a really nice view out over Goleta. So we got to work off that. This is our first image we captured. This is looking toward Goleta. If you look at a magnified part in the bottom, you can see the palm trees down near Goleta Beach. And in the top, the whole image is shown. Now, you could say, why the funny colors? We tried taking regular color images and they were okay. They were color images. They looked all right. But one thing interesting about the 8 different bands we have is that the near infrared bands are such that trees are no longer green. Trees are as white as snow in the near infrared. So the trees become very bright. And this is a false color image where we used, I believe the red channel and the green channel were both in the near infrared. Makes for an interesting color combination. And that's Goleta Valley Junior High School down in the foreground below us. Now, here's another image captured from North Fairview Avenue up near where I live. I have a neighbor with a good view. And once again, it's false color. The near infrared channel was represented as red here. And so all the trees, which are bright white in the near infrared, come across as very red. You might notice some mountains in the background in the left are dark. And that's interesting because those mountains had been burned over a previous year in a big wildfire. And the reason they're dark is there's no trees there. That's just burned over. Otherwise, it would also show up as red. And we had to take a picture from Santa Barbara with the cruise ship import. Of course, that day was foggy, so I couldn't get a very good true color image. You'll notice some funny colors around the leaves that are in the foreground, and that's because we have a push broom array. The array is vertical, scanning horizontally, and the red, green, and blue channels are slightly spatially offset from each other. So you get interesting colors on things that are close. Or things that are blowing in the wind has the same effect. We're a little company. I didn't have all the sophistication that a big aerospace company might have. So some of our testing was a little unorthodox. One of the problems with CubeSats is they're so small. You're basically flying a compass needle, and almost every satellite has some residual magnetic fields, because in our case, we have solenoids. Sometimes you have motors, and these things all have magnets in them. So you end up with a residual magnetic field, which will eventually cause the spacecraft to turn. And the spacecraft has a limited ability to counteract this. So we needed to know what it was. So this was some early testing to look at magnetic field. This is our shutter in the background. So you'll notice when the shutter deflects, the magnetic field moves over. And we go the other way. We have two solenoids, and we purposely made them operate in different directions so the magnetic field would cancel out. But one thing you may not have noticed here is at the beginning of this process, we were a little bit to the left of the south mark. And at the end of the process, we're a little bit to the right. The magnetic field changes. The solenoid has residual magnetism. So fortunately, that turned out not to be a problem at the spacecraft level. We also worried about light leaks. I don't know if any of you have worked on space instruments before, but you typically test them in darkened labs, and you carry the thing around on a pillow, and you're very careful to keep it absolutely clean. But the reality, the way these things are used is you put them on a rocket and you shake the bejesus out of it, getting it up into orbit. And being in orbit is like flying above a cloudlit Earth, is like taking measurements next to a snowbank on a sunny day. It's extremely bright. And I had to worry about light leaks. So we took our computer outside, and Matt had to cover his head up so he could see the screen. And we would hold the instrument, seen there on the card table, in front of a white wall in the sun, and make sure we couldn't see any light. Fortunately, that passed okay. I think a real aerospace company probably could have spent $1 million doing this test. The other problem we have is we're on a little satellite, and it's very power limited. So unfortunately, they can't turn on the attitude control all the time. So most of the time, the spacecraft is just tumbling over end over end. So that means the optics and the sensor will look directly into the sun once in a while. So we had to make sure the CCD could handle looking at direct sunlight without being scorched. So I had to do that test also. Anyway, finally came launch day. We delivered in July of 2017 and December of 2018. We were finally integrated onto a SpaceX rocket to be launched from Vandenberg. The booster was a reused booster. I think it was the first one they ever reused, and that's why it looks like it's kind of blackened and charred. There were a total of 64 satellites on this mission going into space. I think 45 of them were CubeSats. So we were basically launched into space, and all 45 were popped out in the space of 20, 30 minutes. So it was like a cloud of CubeSats. Very difficult telling who was who for a while. The instrument at this point has now been in orbit for 18 months, and we're getting some good images down. This has been a geography lesson for me. You'll see the full-size 1800 by 6000 image on the left, and a detail in the middle. This is the Palk Strait, which is actually the straits between India and Sri Lanka. So it's a very colorful scene. And we overflew an island in south of Indonesia at about the same time as Modus Terra. So we have a chance to compare a Modus Terra image with a Hawkeye image taken within an hour at the same time. As you can see, we have about 8 times better resolution. And that's because we have a lot smaller field of view. And our instrument is nice and smooth, whereas the MODIS image shows some horizontal chattering going on. And anyway, we worked really hard to make sure we didn't have any of that. The big difference here, though, is MODIS Terra cost $240 million, and we cost $730,000. I mentioned before the instrument has 8 spectral bands, and a lot of this is to remove various artifacts. One of the obvious ones is you get sun glints off the ocean. Of course, there's always waves, and the sun is, the instrument captures images near noon. So unless you're lucky, there's always some amount of sun glint coming off the water from the micro ripples and such. But fortunately, the near-infrared band sees sun glint almost exactly the same as our green band does. But yet the near-infrared band doesn't penetrate into the water at all. So you basically subtract the near-infrared band from the green band, and you get the result here, where the sun glint lowers your contrast on the left, but when you remove it on the right, the phytoplankton chlorophyll features stand out much more strongly. And here's the color image. This is Western Australia. A lot of interesting phytoplankton in the water. And also different bands highlight different features. As I mentioned, the green will penetrate deeper into the water than the infrared. This is Hangzhou Bay in China, which is fairly close to Shanghai. And I think this is the Pearl River Delta is coming out here, one of the major rivers. And on the left, you can see what it looks like in the green. And on the right, the near infrared. Excuse me. These swirls coming down top to bottom are probably some sort of smoke in the atmosphere. And the color image here shows that there's a lot of sediment in the water. One of the important things about our instrument is it works over land as well. A lot of times ocean color instruments don't have good sensitivity over land because they're designed for the ocean and they purposely let the land saturate. But our instrument does not do that. So this is a picture taken while flying over Australia. They were trying to catch Alice Springs and Ayers Rock, but they missed. Speaking of missing, things don't always work out just like you'd think. Turns out our big problem on the instrument since it's been in Earth orbit is spacecraft stability. This is a challenge for everyone to figure out where in the world these 3 scenes are captured. I'll help out. The one on the left is over the Persian Gulf, and we caught the Earth's limb. That's the wavy line you see. So we missed the ground by 70 degrees, close. And the picture in the middle is actually Northern California. And we get a number of images with what we call the swirlies, and this is one of them. And the one on the right was actually Baja California, but we managed to wing the Earth's limb at the same time also. So they make for sort of an artistic effect, but hard to get much good data out of one of these. However, sometimes it works great. And this is a picture taken over Namibia showing the sand dunes. This is one of the better images we've captured. And another picture looking out over Northern California. And this one was very stable also. We haven't figured out what's causing the uncertainty in spacecraft attitude control. It's still being worked on here after 18 months, but we're not really sure what's causing it, but closing in on it. This is a picture of the Caspian Sea, which must have a lot of fertilizer runoff going on or something. There's a tremendous amount of algae in the water. In Encounter Bay, Australia, you can see to the left of center a city area, and I believe that's Adelaide Australia. Australia seems to be a good spot for having clear weather. You wouldn't believe how cloudy the world is until you start trying to take pictures of the ocean. And finally, the Gulf of Carpentaria, Australia, which is near Darwin on the northern coast. A lot going on in the water, and the ocean currents and phytoplankton distributions reveal themselves very well. So lessons learned from all of this. Well, I lost quite a bit of money, but I think that's the first rule. Don't start an aerospace company when you're 65 if you're not prepared to go in the hole a bit. There was an amazing amount of bureaucracy you wouldn't expect. Since we view the Earth, we needed a permit from the National Oceanic and Atmospheric Administration, since we are a remote sensing satellite. And we have a transmitter on board. Of course, we need a radio to get the information to the ground, and we basically had to get an FCC license, no different than if we were a radio station in Tennessee or anything. We had to have a deorbit plan to make sure the satellite would come down within a period of about 25 years. And there is enough drag, it will come down within about that time frame. And it's kind of funny, I mean, we built this thing here in Goleta and it launched from Vandenberg, but it had to go to Glasgow, Scotland to get integrated. And so even though we launched from Vandenberg, we need an export and import certificates to get it to go back and forth. And the one that I thought was really kind of ridiculous was we had to guarantee spacecraft control is from USA soil. And that's so they can turn off the instrument's remote sensing capability in case of war with Scotland. Each one of our pixels is 400 feet on a side, so it's not like you can recognize tanks or anything with our instrument. But this was very important. We had to do it. Fortunately, NASA is involved in it. NASA is analyzing the data. All of these pictures were generated by NASA Goddard Space Flight Center. And when we do the occasional downlink, when we're not troubleshooting attitude control problems, we use NASA's downlink stations. It's still operational. We're still working it. The next download, I think, is next week. And I hate to say it, but I still haven't gotten a picture of Lake Atitlan. I'll turn it back over to you, Stephanie, to stop the sharing.
Yeah, great. Thank you so much. Do you want me to leave this slideshow up in case there's questions for specific photos? And we can go back?
You can.
Okay. So thank you very much. Not only was that very informational, but I really enjoyed your humor as well. I know no one could hear me, but I was giggling quite a lot. So thank you very much. So we're going to open up the question and answer portion. So if you have questions, go ahead and type them into that Q&A at the bottom of your screen, and they will come to me and I will ask them to Alan. While those are coming in, I have a couple. So if you could expound a little bit, how many photos, or is it just one image, would it take? Like, I mean, you could scroll back a couple. If you look at that, like the coast of Australia, how long does it take to do that? Is that one image, like it took it 1 second, or is it multiple?
No, we're a push broom scanner. So on the left, you see the entire image. That takes 2 minutes, 2 minutes of spacecraft travel time. And it's because it's 8 bands, each band is basically a each band is the equivalent of about, it's been too long, about 12 megapixels, but we have 8 bands. So it's about 100 megapixel image. We use image compression to get it down to 100 megabytes per image.
Okay.
And as of this date, after 18 months, I think we're only at about 140 images total, of which, 10 or 20 are really kind of good, and the rest have some issues because of the attitude control.
Okay, so before we get into other questions, there's one that would be very helpful, which is what is the attitude control system and what's a gyroscopic?
Okay, it's actually got a lot going on for a spacecraft the size of a loaf of bread. It has sun sensors that determine where the sun is on 3 faces. And if you know where the sun is, you have a pretty good idea how you're oriented relative to Earth. They also have a magnetometer which senses the Earth's magnetic field. And that helps provide one other dimension that's enough for them to then figure out how you're oriented. And the spacecraft has reaction wheels that can spin up and cause the spacecraft to rotate a little bit. We don't have any thrusters or anything like that. We're too small, and expendables mean you don't last that long. So we don't have anything like that going on. So those are the primary control, the reaction wheels using sun sensors and magnetometers. It's interesting. You would think you could just position this thing and it would just stay oriented, but it's not. If you had this thing perfectly stable and you came back an orbit later, it'd be spinning at around a degree a second or something. I mean, there's some atmospheric drag, there's some magnetometer torque residuals. It just doesn't hold its position.
And I know this may be silly, but how fast is a degree a second? Like in our space, is that quick or is that not?
Most people would consider that pretty slow. That's one rotation. That's one rotation every 6 minutes. So that sounds pretty good. But our resolution is 1/80th of a degree. So a degree per second is problematic. That's at the high end of what we can tolerate. So that's kind of what we're trying to deal with.
And then gyroscopic, and is your system solar powered, or how is it getting its energy?
It has 2 solar panels. It had 4, but 2 never deployed. So 2 solar panels are powering the instrument. It has a battery on board about the size of a pack of cigarettes. And the solar panels keep the battery charged up. And we only take one image in orbit at most because there's not enough power to take more. It's all very small.
And from Judith, did you have to design the machine to deliberately drag to a decaying orbit in around 25 years, or was that not necessary in the design?
Well, we had to do the calculation to show that it would probably come down. But a lot of the newer missions are being hit with specs where they have to basically bring the satellite down faster than that. And just if you're curious, the favorite technique for a CubeSat is you have like an inflatable balloon. At the end of your mission, you inflate the balloon like an airbag, and the extra drag helps bring the spacecraft down a lot quicker. So it's techniques like that they use to deorbit and get things down from space.
Then do you recover it, or do you just consider it debris?
No, it just burns up. It's all gone.
Okay. Hawkeye is scanning the Earth completely in how many days and orbits?
It rotates, it goes around the Earth once every 90 minutes. It's moving at 5 miles a second, so it's moving pretty fast. And so every 90 minutes, it orbits in what's called a sun-synchronous orbit. So it crosses over the equator at 1040 on every orbit. And then it takes about 18 days. Let's say it went over our head today, then in 18 days, it would repeat and go back over our head again. So the orbit kind of wanders slowly around the Earth.
And again, you have only then got around, did you say 180 usable images?
140, 150, of which usable is a relative term here. But we're getting it.
Yeah. Who is using it? What's the data being used for, specifically different researchers?
Well, the plan was to get the spacecraft commissioned to where NASA can open up. There's a lot of bureaucracy at NASA, and in order to use the entire NASA Deep Space Network to download images, you have to have a reliable satellite, and we're not quite there yet. But when they open it up to being able to use the tracking stations in Alaska, then we can get down many more images, and they'll probably start taking images on every orbit. So that'll be 18 images a day. And I think this is mainly a proof of concept to demonstrate to people that you can get good ocean color out of something the size of a loaf of bread. And with the thought in mind that maybe somebody would put up a constellation of these, 20 or something like that. And it would be a lower cost alternative to ocean color. The next ocean color instrument replacing Modus Terra and Modus Aqua is called PACE, and it's going to cost almost $1 billion. And you could imagine it's probably pretty affordable, more affordable to put up 20 or 50 little guys than $1 billion mission.
Yeah, most definitely. So we have a couple of questions that kind of piggyback on that. So from Dennis, have you had any requests specifically from researchers doing applied research in oceanography or other disciplines that you could provide those images to support their research projects? And if so, what research would that be?
The satellite is not yet operational, so they're not yet accepting requests, so to speak. But this would probably be mostly concerned with coastal areas. I think that would be more interesting. Lakes, lakes, they do tend to get planked algae blooms like in Lake Erie every year or such. And I'm sure there'll be some people interested in looking at lakes, maybe not so much rivers. I'm mainly a hardware guy here, so I don't really deal with the science aspects of what can be done with the images. So, but I think the simple answer is they're waiting for it to become operational.
And then another one with the photos. Given the error rate on viable pictures, how many more viable pictures do you expect to download in the remaining lifespan of the satellite?
The satellite can only hold 18 images at a time. And NASA—
And then it downloads to you.
At a time between downloads. And we're only downloading every 18 days now. So that's not a lot of images. So what happens now is that we'll take an image and NASA will look at the corresponding MODIS image and say, oh, that was cloudy, let's erase it. So we erase it, or we do get telemetry down that tells us whether the pointing was stable. So if it was a cloudy day and the pointing was no good, the image gets deleted and they take another one. So given that scenario, it does take about 18 days to get 18 images. So that's, I forgot the initial question, but that's how the
lifespan. So 18 times 360 times 25.
Right. Now we were supposed to have a 2-year mission life. We're at 18 months now, and the attitude control is not fixed yet. So I don't know. I hope we have some lifetime by the time all this starts working better. But can't do anything about it now. There is a second instrument that can be integrated and put into orbit also, basically the same as this. So the idea is to get all the problems figured out on this one, and then we can launch a second one and maybe get 2 years of good imaging out of it.
Thanks.
Each launch costs about $275,000, by the way, for those who are interested.
Even if you're piggybacking on the SpaceX. So
yeah.
Wow.
That's the discount rate, even if you're sharing the mission. Ride share, they call it.
So another question, this one's from Sabina, is the GPS useful and how?
The GPS has never worked. They apparently have a broken antenna wire. So it would be very useful if we had it. But right now we rely upon Air Force tracking stations, which apparently constantly monitor everything in orbit and can tell you exactly where you are. And they relay that information to NASA, which relays it on to Glasgow. And so we have to use that information since there is no onboard measure.
Thank you. Tom says he has a couple. So one is Will there be better scanner arrays in the future, and is better needed, or are you happy with this?
It's working well. However, the company that made the array that we're using went out of business basically in March. They made CCD sensors, and CMOS has basically killed CCDs. So now our low-cost CCDs are no longer available, so I can't make another one if I wanted to. There's some other options out there, but they're different. It would be kind of a lot of redesign to start over. One of the things, if you don't deal with electronics much, we ran into this all the time at Santa Barbara Instrument Group, is whatever you designed into your instrument or gadget, 3 years, you won't be able to buy it. So you're constantly redesigning to get around the parts obsolescence issue. And this is no different.
Thank you. A few more from Tom. So this says the UAE Mars orbiter Hope will be looking at color off the ground and atmosphere. Do you think it is a similar scanning system?
They're using a similar CCD array. They would be using what's called an area array, which is what's typical in a digital camera. It just takes a picture. You don't have a push broom array. I thought the spacecraft would be stable enough we could get away with a push broom array, but in the case of that little UAV at Mars, no, they'll just take a picture. They'll probably take a 10 millisecond snapshot and then hope things don't move too much over that long a period.
Okay, from Chris, what is, or if there is, any danger of collisions when the first satellites were all released together?
They released them 30 seconds apart, and they pop them out with I think it's 5 feet per second type velocities. And the hope is they just don't come too close together. One of the interesting problems, NASA flew a CubeSat mission once, and they put magnets in the CubeSats to keep them in the hope that they would line up with the Earth's magnetic field. But they popped out 2 satellites at the same time, and they basically both had magnets in them, and they came together and stuck. And ever since then, they learned their lesson. They space the satellites a lot farther apart.
That's an expensive mistake.
Yeah, that was embarrassing for somebody. So the bottom line is they're somewhere on the order of 100 or 200 feet apart, and then you just cross your fingers.
And does it change based on the size of the satellite, like the rate at which they're orbiting? So do they have to plan that out?
Well, I don't know much about the larger satellites. I'm sure they were deployed with a little more time between them, because they were considerably more expensive.
All right, great. Next one is at what resolutions do the instruments take the pictures?
130 meters per pixel. And we have a little blur, so these tiny little clouds you see in this image would be on the order of 300 meters across, 1,000 feet. Wow. So our resolution is still very low compared to Google Earth or Landsat or any of these other missions, but it's, as I mentioned, it's 8 times greater than any of the other ocean color missions flying.
All right, a few more questions. So did Adriana's attempts to protect the Guatemalan lake succeed? And then you already answered this, but did you take any pictures of it? So not yet for that.
We've taken images of it twice, and both cases it was not recognizable in the result.
And then how is the lake doing?
It turns out in Guatemala, you only get clear weather January, February, and March. So I'll wait until January, and then I'll start asking NASA to try again.
Got it.
Maybe we'll get one.
And then the last question that we have is, are you still doing amateur astronomy? What camera do you use, or what would you recommend for someone to buy?
Well, it's kind of a sad story. We had a fire up here, the holiday fire. I live up on North Fairview. and my observatory burned to the ground along with everything in it. I had a pretty nice setup, but it just turned into molten aluminum and broken glass.
Oh.
And you know, I've kind of gone on in a different direction now. I do my astronomy looking down instead of looking up. So it's kind of been busy doing other things. I still dabble in it. It's funny, the ex-marketing person for SBIG is now the marketing person for QHY. If a person wants to get involved in CCD imaging and do something simple and cheap, the QHY 174 is a great little camera. Anyway, and SBIG still exists in Ottawa, Canada, but the cameras are designed more for professional amateurs, people who want the ultimate performance. And they're rather expensive. They're in the $10,000 range. But the QHY 174 mono is just a great introduction to digital imaging.
And Tom, to piggyback off of Alan's remarks, there's an astronomical unit based in Santa Barbara. So if you're just getting into astronomy, they, in pre-COVID times, I'm not sure about what they're doing right now, but they have astronomy evenings where they'll actually all set up their telescopes and view. And we have an astronomy department too. So if you have further questions or want to get involved, by all means. Oh, he's the webmaster for the Santa Barbara Astronomical Unit. So you know about all of that. So great. Thanks, Tom. All right. So it looks like we do not have any more questions and we are about out of time. So that was perfect. Alan, thank you again so much. That was a wonderful talk and beautiful images and job well done. So we look forward to more.
Thank you, Stephanie.
Yeah. So next month we have Jenna Roll. She is our team programs manager and a geologist, and she is going to be discussing what is a dinosaur. And that is a very fascinating topic, and I'm sure that everyone will learn a lot because I learned a little bit from, we had many, we called them Ed Talks to keep us all kind of educated and connecting with each other when we were at home a few months ago. And this was a fantastic talk that she is now going to be expanding for us for Science Pub. So please join us next month, August 10th. I hope until then, everyone stays safe and well. We will see you then. Bye. Thanks, Alan.